In this video, I want to talk about integration. I want to talk about what it is and what it's useful for. So integration is all to do with areas. So for example, if we were given an area like this, so we're given a straight line, a linear function, and we were asked to find this area in here. So the area under that line between the values of A and B. Or here, if we've got a straight line, we've got to end up with a triangle here between A and B. Or this one here, and we end up with a trapezium. Now, because they're all bounded by straight lines, we could just use our standard area formulas for rectangles, triangles, and trapeziums to find those areas. Now, that also works if we had something like a semicircle. If we had a semicircle going between the x values of A and B, and we wanted to find the area underneath that, we could just use the area formula for a circle and halve it. So all those things we can just use our standard area formulas for. But where integration comes into it is when we have a more general curve. For example, here we've got this black curve, and we're trying to find the area underneath that curve between A and B. So this whole region in here. Now, because it's a curve, we don't have a standard formula that we can use for it, but we can approximate it using a rectangle. Now, if we just take this height here, draw a straight line across there, and find the area of this rectangle, you can tell that that's not going to be very accurate because we've missed this whole chunk up there. Now, we can get more accurate though if we were, say, to split it in half. So if we were to split that section into two regions and find the height of two different rectangles instead, so we've got this rectangle here and this rectangle here now, that's getting more accurate again. If we were to split it even further, so let's split those sections down there, find those rectangles as well. So we've got 4 rectangles we're finding the heights of now, sorry, the areas of. Then it's getting more and more accurate each time. Now, if we were to split it into tiny little rectangles, lots and lots of tiny little rectangles, we're going to get a really accurate approximation of the area. So the idea is we're going to calculate the areas of lots of little tiny strips and add them all together to calculate the area of that whole region. So let's have a look at just one of these strips. So I've got a red strip coming down here. Now that's at an x value of x, and then its width is this delta x. So that rectangle, its width is delta x, so its x value at the start is just x, and its x value at the end of the rectangle is x plus delta x. Now, because that rectangle is infinitesimally small, that delta x is representing a really tiny number. So because it's infinitesimally small, the height of that rectangle will be f of x. And even though over this side, theoretically, it looks like it's a little bit taller, because delta x is tiny, it's going to have a height of f of x as well. All right, so we're going to add up all of these areas. So we need to know the area of one strip. So, oh, hang on, wrong button. So the area of one strip. So we're saying that if this was infinitesimally small, obviously I can't draw it as skinny as we want it to be, so it does look like it changes height here. But if we could draw it and imagine it being infinitesimally skinny, then its height would be f of x, its width would be delta x, and it would be the shape of a rectangle. So the area of one strip would be equal to that f of x, so the height of that rectangle, multiplied by the width of that rectangle, which is that delta x. So that's one rectangle. But we want an infinite number of those rectangles all the way along, all added together. So adding up all of the areas of all of those strips, we would get the area of the shaded region, which is just this whole section which isn't shaded anymore, but that whole section in there between A and B and under that curve. So the area of the shaded region would be equal to the sum from x equals A to x equals B, so from x equals A to B, there are bounds, of f of x times delta x. So we're going to find the areas of all of the little rectangles between A and B and add all of them together. Now, to get those rectangles infinitesimally thin, we want to take the limit as this delta x approaches 0, so as it gets smaller and smaller and smaller, because that's what's going to make our area calculation accurate, is when those rectangles are infinitesimally small. So that means that we want our delta x to be approaching 0. So that means now that our area is going to be the limit as delta x approaches 0 of that area formula we had before. So we've got sigma from x equals a to b of f of x delta x. So this whole thing is calculating the area under that curve between a and b. So that's the calculation that we need to do, but we're going to introduce some new notation. So instead of writing that whole thing out, what we're going to write is this symbol here, which looks like an S but long and skinny, from A down the bottom to B of f of x. And instead of writing delta x now, we're just going to change that to d of x. And the way we read this is the integral from a to b of f of x with respect to x.